With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello, in this question given the rate constant K for the order gas phase decomposition of ethyl iodide C2H5I gives the C2H4 plus HI is the 1.60 into 10 raised to the power minus 5 second inverse at a 600 Kelvin and 6.36 into 10 raised to the power minus 3 second inverse at a 700 Kelvin. Calculate the energy of activation for this reaction. So in this question, we have to given the order of a gas phase decomposition of a ethyl iodide at a temperature 600 Kelvin. The rate constant is a 1.60 into 10 raised to the power minus 5 second inverse. And at a 700 Kelvin, that is a 6.36 into 10 raised to the power minus 3 second inverse. We have to calculate the activation energy. So in this question, we have to given the rate constant K at a temperature T1. So we can write the rate constant at a temperature, rate constant at a temperature 600 Kelvin. Rate constant at a temperature 600 Kelvin. Consider that is the rate constant K1, that is equals to 1.60 into 10 raised to the power minus 5 second inverse, and a rate constant K2, rate constant at a temperature 700 Kelvin, rate constant at a temperature 700 Kelvin, rate constant at a temperature 700 Kelvin, that is the rate constant, that is the consider that is the rate constant K2, that is equals to 6.36 into 10 raised to the power minus 3 second inverse. And we can write, we have to given the temperature T1, our temperature T1, that is equals to 600 Kelvin. Temperature T1 is the 600 Kelvin, and temperature T2 is the 700 Kelvin. Temperature T2 is the given, that is a 700 Kelvin. Temperature T2, that is a 700 Kelvin. We have to calculate the change in activation energy. So if we have to given the rate constant and temperature, so the relation between rate constant and temperature at a different temperature at a different rate constant we have to give. So the relation is the using the according to the Arrhenius equation, log K2 by K1, log K2 by K1, that is equals to log K2 by K1, that is equals to EA. EA is the our activation energy upon 2.303 R 1 upon T1 minus 1 upon T1 minus 1 upon T2, where EA is the activation energy, EA is our activation energy, and R is the our gas constant, R is the our universal gas constant, and its value is the universal gas constant, its value is the 8.314 joule per mole Kelvin. So now we know that the value of K2, K1, T1, T2, 2.303 R. Now put in the formula, we get log K2 by K1. So log K2. So our K2 is the, we have to given the value of a K2 is the 6.36 into 10 raised to the power minus 3 second inverse. 6.36 into 10 raised to the power minus 3 second inverse divided by log K1. The value of a K1 is a given 1.60 into 10 raised to the power minus 5. 1.60 into 10 raised to the power minus 5 in second inverse. So now second inverse to second inverse get cancelled, that is equals to EA activation energy divided by 2.303 into R, that is the 8.314 4 joule per mole Kelvin, joule per mole Kelvin, whole divided by 1 upon temperature T1. 1 upon temperature T1 is our 600 Kelvin minus 1 upon temperature T2, that is the 700 Kelvin. That is our 700 Kelvin. So now the calculate from this part. So log calculate from this part, we get the log that value is the 2.60. 2.60 log this value is a 2.60, that is equals to EA, activation energy, divided by 2.303 into R, 8.314 joule per mole Kelvin, joule per mole Kelvin, into calculation from this part, we get 100 in Kelvin, 100 in Kelvin, whole divided by 600 in Kelvin into 700 in Kelvin. So now this Kelvin to this Kelvin get cancelled, and this per Kelvin to Kelvin get cancelled. So now the calculate from this part, rearrange the term, we get the activation energy EA. Rearrange the term, we get activation energy EA, that is equals to 2.60 into 2.303 into 8.314 into 600 into 700 whole divided by 100. Whole divided by 100, and the unit is the left, that is a joule per mole. So now the calculate from this part, we get the activation energy EA, that is equals to 2090 86.80 in joule per mole. And when converting kilojoule, so we divided by 1000. So now the activation energy in kilojoule per mole, that is a 209.08 in kilojoule per mole. So this is the our change in activation energy. So our activation energy in joule per mole is a 209086.80 joule per mole, and in a kilojoule per mole, that is a 209.08. So I hope this answered your question. Thank you.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.